Well, hello there. Today we're going to be talking about simple machines. We want to be able to distinguish between the 6 simple machines, their attributes, and their components. Those are going to be the main things that we are discussing. We're also going to be discussing the mechanical advantages. With this, we won't really be getting into the drive ratios, but we'll be discussing those things right there today. Once again, the lever, wheel, axle, and pulley is what we'll be discussing today. Simple machines. The simple machines we're going to be discussing are the lever, wheel, and axle, and the pulley. There are 6 simple machines. We're just going to be covering the first 3. The next ones will be discussed later on. Mechanical advantages, the ratio, the magnitude, the resistance, and the effort force. So when they say ratio, we're talking about fraction here. And you're talking about, here we go, so fraction, the ratio of the magnitude of the resistance. So we're talking about resistance of resistance force over the effort force. Another way doesn't deal with forces, it deals with distances. All right, so it's the distance traveled by the effort, so it's just the opposite. It's the effort distance over the resistance distance. Mechanical advantage. Here's an example. A mechanical advantage of 4 to 1 tells us about a mechanism. Magnitude of force. The effort force magnitude is 4 times less than the magnitude of the resistance force. So what this tells us here then is that this simple machine, if we were to say, once again we're talking about force, so we're going to be using this top one up here. There we go. That top, oh, we don't like that, that looks alright. So we're using the top one with resistance force and effort force. So the resistance force is going to go on top, and we maybe have a resistance force of, let's say, 1 pound, and an effort force, I got to backtrack here again. The resistance force, yes, is 1 pound, and the effort force, backtrack that again, I keep saying this wrong. The resistance is maybe 4 pounds, and the effort force is 1 pound. I kept thinking of that vice versa. My apologies. But what this means is it's 4 times easier because of this mechanical advantage. It's for every 1 pound of resistance, or for every 4 pounds of resistance, it only takes 1 pound of effort to lift. Distance, if you notice, distance was down here. It's just the opposite. It's going to be much longer. It's just the opposite, which means, let's say it took 1 meter to lift it. Well, for every 1 meter it takes to lift something or to push something, we're going to have to move it 4 meters, or vice versa sometimes. Work. Work has a simple definition. Work is equal to force times distance. And what I want to make sure I do here is force times distance. This is our equation for work. Sometimes we just simply say W equals F times D, but it's the force times the distance. Things I want to point out here, and for those of you who have been in physics, this should be just a quick reminder. Notice that the force is parallel to the distance that the object is being moved. And what I mean by that is the object is moving in this, is being pushed in the same direction that it's moving. An example we gave that would be opposite of that quite often would be if I was walking around carrying my books. The books would be moving forward, but the force would be going up, and they'd be perpendicular, which means they wouldn't count. Work is the product of the effort times the distance traveled will be the same regardless of the system mechanical advantage. So the work should always be the same, and that's really if the things are frictionless. So kind of moving all over the place here. I didn't mean to quite hit that button. That's if they're frictionless. So that's not always the case, but it is when they're frictionless. Mechanical advantage ratio. 1 is the magic number. If the mechanical advantage is greater than 1, that tells us it takes less effort force is required to overcome the resistance force. It takes greater effort distance. If the mechanical advantage is less than 1, it means it's going to take greater effort. So if you had down here, let's say a mechanical advantage of 1 to 4, all right, it means it takes greater effort. Right, this is our resistance, and this right here is our effort. So we're having to push or pull, let's say it's a pulley, we have to pull down with 4 pounds to lift something that's 1 pound. That's if it's less than. Right? There we go. Alright, ideal mechanical advantage. This is a little bit difficult to read, but I think we can get through it. Ideal is a theory-based calculation. That's what I want you guys to understand. It's theory-based calculation. It means we're not going to use actual measurements. We're going to say in theory, in a frictionless situation. Friction loss is not taken into consideration. And here's our examples of it. IMA, we're using IMA uses simply the distance. All right. And it's the effort distance over the resistance distance. But IMA is distance. And I don't know how else to tell you that, except right there it is. IMA uses distance. Actual mechanical advantages. In this situation, frictional losses are taken into consideration. Right? That's important to realize. Actual mechanical advantage, then, is going to be using force. Again, IMA uses distance and AMA uses force. Real-world mechanical advantage. Can you think of a machine that has a mechanical advantage greater than 1? Most machines are going to have a mechanical advantage of greater than 1. An inclined plane has a mechanical advantage of greater than 1. An inclined plane could be like a ramp. It's out of maybe someone who's on a wheelchair. You're trying to get them to a higher situation. Most pulleys, and not really just a simple pulley, but a block and pulley system, has a much higher mechanical advantage than 1. Can you think of a machine that has a mechanical advantage less than 1? Well, as we said, a single fixed pulley does have, it actually has an ideal mechanical advantage of 1, and after you take friction into consideration, it's going to have an actual mechanical advantage of much less than 1. Alright, start with some levers. A rigid bar used to express a pressure or stand a weight at one point of its length by the application of a force at the second and turning at a third on a fulcrum. So, and that's what we're talking about, giving all these different examples here of levers. First class lever. First class lever is a teeter-totter. The fulcrum's in the middle, and the effort and resistance are on opposite sides. You can copy all that, or you can copy down what I said. This is the only one, I will point this out, that can have a mechanical advantage that's greater than or less than 1. It can be either way, depending upon how you set it up. Second class lever. All right, second class lever. The way I always remember this is there's an acronym called FREE. FREE. And what that stands for here is fulcrum, resistance, and effort. And in a second class lever, it's always free. And what that means here then is it's going to be easier. You're going to have a mechanical advantage that's greater than 1. A wheelbarrow is a great example of a second class lever. This up here would be your wheel. This right here would be the payload you were trying to lift. And then right back here, you've got your handle. So wheelbarrow is a second class lever. The last one here is a third class lever. A lot of times machines, or weightlifting machines, are set up by third class levers so that you have to put a lot more resistance into them than the effort. They can use a very small piece of resistance, and you'd have to apply a lot of effort to lift it. Third class levers always have a mechanical advantage of less than 1. And again, this is for a lot of times this would be used for weight machines, just for real simply put, to give you muscle heads an example. Okay, I'm going to hurry through this here. A pulley is a lever consisting of a wheel with a groove in its rim, which is used to change the direction and magnitude of a force exerted by a rope or cable. There's lots of examples of pulleys. I don't think I need to go into a lot of detail with that. There are some pulleys. We have a fixed pulley, which is over here on the right. It has an ideal mechanical advantage of 1, and its AMA, I'm going to write this down, its AMA, actual mechanical advantage, would be less than 1. Why? Because of friction. The other one is a movable pulley. It's a second-class lever with an ideal mechanical advantage of 2, because it's going to be moving. So fixed pulleys have IMAs of 1 when it comes to mechanical advantage, and movable pulleys have AMAs or IMAs of 2. Now, the next thing and last thing I want to really go over here with is how we would talk about pulleys in combination. What kind of ideal mechanical advantage we get? We're up here at the top. Notice that both of these are fastened up here at the top, so realistically, these are both what we call fixed. So this is an ideal mechanical advantage of 1. That is an ideal mechanical advantage of 1. Down here, this is one that's going to move, so it would have a mechanical advantage of 2. And this one has an ideal mechanical advantage of 2. So to find the IMA, what we do is we do a little math. We multiply them. 1 times 1 times 2 times 2 gives us an ideal mechanical advantage of 4. On the other side, notice that all 3 of these are going to be moving. So that's 2, 2, and 2. And when we multiply that, the movable pulleys here give us an ideal mechanical advantage of 8. Hey, well, that's everything for today. I'll catch you on the flip side.